General characteristics of lanthanoids. Lanthanoids are all metals. They are soft metals, silvery white in color, and they tarnish rapidly in air. When atomic hardness of lanthanoids increases with the increasing atomic number. Samarium is very hard. Samarium is steel hard. Hardness of samarium is comparable with the steel. Samarium is steel hard. Melting point of lanthanoid ranges between 1000 to 1200 Kelvin. Samarium melts at a higher melting point. For samarium, the melting point is 1623 Kelvin. Samarium is very hard. They have a typical metallic structure and are good conductors of heat and electricity. Now, color of lanthanoid ions. Most of the lanthanoid ions are colored in their +3 state because of the presence of unpaired F electrons. Unpaired electrons in the F atomic orbital. This is because of color of the lanthanoid ions are due to the transition of F electron from lower energy F orbital to higher energy F orbital. That phenomenon is called F of transition. So, color of lanthanoids is due to F of transition. There are ions which are colorless. For example, lanthanum 3+, lutetium 3+ are colorless because they have lanthanum 3+ is colorless because 4 of 0, no electron in F atomic orbital. Lutetium 3+ is colorless because it contains 4 of 14 electronic configuration, no unpaired electron. All the electrons are paired, completely filled F orbital configuration. Another example, cerium +4. Cerium +4 is also colorless because it has got 4 of 0 configuration, empty F atomic orbital configuration. And most of the lanthanoid ions are paramagnetic. Paramagnetism due to unpaired electrons. And paramagnetism is maximum in neodymium. Neodymium, the paramagnetism is maximum. And here also exceptions are there. Some of the ions which contain empty 4 of orbital or completely filled 4 of orbitals which contain no unpaired electron are diamagnetic. Examples are lanthanum 3+, lutetium 3+, cerium +4. All these ions are diamagnetic because they contain no F electron or they contain completely filled F electron. The first ionization enthalpy of lanthanoids are comparable with first ionization enthalpy of lanthanoid, delta Hi1 of lanthanoid is 600 kilojoule per mole, and the second ionization enthalpy is 1200 kilojoule per mole. It is comparable with the ionization enthalpy of calcium. So, lanthanoid elements resemble in their chemical behavior to calcium and other alkaline earth metals. The initial members in the lanthanoid series, initial members of lanthanoids are anthanoids behave like calcium, but towards the end of the lanthanoid series they resemble aluminum in their properties. That means lanthanoids are reactive. Their ionization enthalpy values are similar to that of calcium. So they behave like a calcium, and some members behave like a aluminium. The third ionization enthalpy values, delta Hi3. The variation of third ionization enthalpy values of lanthanides are irregular. This is because of the extra stability of empty, half-filled and completely filled f electronic configuration. Just like we explained the irregular variation in the ionization enthalpy of transition elements. Here also the irregular variation in the third ionization enthalpy can be explained on the basis of empty, extra stability of empty, half-filled and completely filled electronic configuration. Third ionization enthalpy of lanthanum 3+, gadolinium 3+, lutetium 3+. Third ionization enthalpy values for these ions are exceptionally low. This is because of their extra stability. Lanthanum 3+ is having 4f0 configuration. Gadolinium 3+ is having 4f7 configuration, half filled. Lutetium 3+ is having 4f14 completely filled. Because of this extra stability, the formation of these ions are very favorable and hence require only very less amount of energy. That is delta Hi3. Third ionization enthalpy values of these three ions are abnormally low. So chemical reactions as we already told resemble alkaline earth metal calcium, and some elements behaves like aluminium. And the chemical reactivity of lanthanide elements can be explained as lanthanoids react with Ln is the general symbol for lanthanoid. They react with acids and liberate hydrogen gas. Lanthanoids react with oxygen and form oxides, lanthanide oxides of the formula Ln2O3. They react with sulfur and form lanthanide sulfides. Lanthanide valency, common valency 3, sulfur valency 2. They react with halogens and form halides, lanthanide halides of the formula LnX3. They react with nitrogen and form lanthanide nitride. Valency of both 3. So they get cancel each other. So Ln is the formula. They react with carbon and form compound of the formula LnC2. In this lanthanoids show valency 2. The lanthanoids react with water and form hydroxide. Lanthanoid trihydroxide. So these are the reactions given by lanthanides. These lanthanide hydroxides and lanthanide oxides behaves like the oxides and hydroxides of alkaline earth metal. They are basic. Then lanthanoids are used as uses of lanthanoids. Lanthanoids are used as catalyst in petroleum cracking. Mixed oxides of lanthanides are used as catalyst in petroleum cracking. A very important lanthanoid metal alloy is called Mischmetal. The name of the lanthanoid metal alloy is Mischmetal. It consists of 95% of this alloy is a lanthanoid metal. 5%, approximately 5% is iron. And trace amounts of, small amounts of sulfur, carbon, calcium and aluminium are present. This is used in a magnesium based alloy to produce bullets, shell, lighter, flint are made from Mischmetal. It's a very important lanthanoid metal alloy. Some lanthanide oxides are used as phosphors in television screens and other fluorescent surfaces to produce light. These are also used for the production of alloy steels for plates and pipes. Uses of lanthanoids.